We now discuss the solution of a problem from the section Linear Algebra, and this problem has appeared in the CSIR National Eligibility Test held in December 2023, and the problem is related to the concepts of vector spaces. And this question is from the part C, that it is a multiple select question. There can be more than one answer, and it carries 4.75 marks, and the question ID is 704071. The given question is, let F be a finite field and V be a finite dimensional non-zero F vector space. F vector space means it is a vector space over the field F. And the field F is given to be finite field, that means a field containing finitely many elements. And V is a finite dimensional non-zero vector space over the field F. Then we have to identify which of the following can never be true. Can never be true. That is, you have to find out a false statement. Right. And we are given four options. Option 1, V is the union of two proper subspaces. Option 2, V is the union of three proper subspaces. Option 3, V has a unique basis. Option 4, V has precisely two bases. Right. Let's now discuss the solution of the problem in detail. We are given V over F, a finite dimensional non-zero vector space over a finite field F. I have already told you, a finite field F means is a field containing finitely many elements. It is a Galois field, in other words. Right. Let's now discuss the options in the serial order. Let us take the option 1. V is the union of two proper subspaces. Is it always true? That's the question. Assume the contrary. That means you assume that V is the union of two proper subspaces. Right. These two proper subspaces, name it as W1 and W2. That is, V is equal to W1 union W2. Now recall a theorem. When W1 union W2 is a subspace, it is a subspace if and only if either W1 is contained in W2 or W2 is contained in W1. If W1 is contained in W2, W1 union W2 is W2. If W2 is contained in W1, W1 union W2 is W1. Right. So what is it? It says V is equal to either W2 or V is equal to W1. That means it says V is a proper subspace of itself, which is not true. So this says V is a proper subspace of V. That means V is a proper subspace of itself. A contradiction. This contradiction is due to your false assumption. That is V is the union of two proper subspaces. W and W2 will never happen. Therefore, your option is never be true. Right. Let's go for the option 2. So we have already noted option 1 is not true. Let's take option 2. V is the union of three proper subspaces. Is it possible? That's the question. So in the following case, this is true. Let F be the finite field containing two elements. That is, F is equal to Z2 under addition modulo 2 and multiplication modulo 2. It is a finite field of two elements where Z2 consisting of 0 and 1. Now let V is equal to Z2 cross Z2, that is the ordered pairs 0, 0, 0, 1, 1, 0, 1, 1. It is very easy to see that V is equal to Z2 cross Z2 is a vector space over the field F of dimension 2. Right. Now let's now consider one-dimensional subspaces of V. First we consider W1 is the linear span of 0, 1. That is, W1 is a subspace containing 0, 0 and 0, 1. W2 is the linear span of 1, 0. W3 the linear span of 1, 1. These are one-dimensional subspaces. That means they are proper subspaces of V. And you can see that V can be written as W1 union W2 union W3. Yes. So in this case, Y can be written as the union of three proper subspaces. This is possible. Thus, V is the union of three proper subspaces. Therefore, the statement that is given in the option 2 is true. Right. Let's move to the option 3. So far we have seen option 1 is not true and option 2 is true. Let's go for the option 3. V has a unique basis. Yes, this is also true in the following case. Take F to be the finite field with two elements. Right. Now consider F over F is always a vector space of dimension 1. So let V be Z2. So V is a vector space over F, that means F is a vector space over F of dimension 1. And B is equal to the singleton set consisting of one element. How many singleton sets are there consisting of non-zero elements? There is only one singleton non-zero singleton set whose element is not zero. B is, and it spans the whole of the vector space and it is linearly independent because 1 is not 0. Thus B is a basis for the vector space V over F, and it has no other basis because there is only one element which is non-zero. So it has a unique basis. So option 3 is also true in this case. Let's move to the option 4. Right, option 1 is not true, option 2 is true, option 3 is true. Let's go for option 4. V has precisely two bases. Yes, this is possible in the following case. Let F is equal to Z3 under addition modulo 3, multiplication modulo 3, a finite field of order 3, where Z3 consisting of element 0, 1, 2. And now consider the vector space V is equal to Z3, that is F over F. It's a vector space of dimension 1. Agree? Now consider B1 consisting of singleton set consisting of 1, B2 singleton set consisting of 2. Both span the whole space and they are linearly independent, therefore they are the basis. Right, B1 and B2, and these are bases, two bases of the vector space V over F, and V has no other basis because there is no other non-zero element in this. So V has precisely two bases. Right. So the option 4 is also true. So option 2, 3, 4 are true. Option 1 is never be true. And we have to find out that option which can never be true. Therefore, the answer to this question is option 1. That is the detailed discussion of the solution of this problem from the section Linear Algebra, which is based on the concepts of vector spaces. I am sure that you have understood the solution of this problem, And I have been doing the videos related to NET examination, IIT JEE main exam, TS set, AP set, etc. examinations. I am sure that you like my videos. You express your liking by posting a liking icon, that is the thumbs up icon in the channel, and share my videos with your friends who are aspiring to clear this exam. If you have not already subscribed, please subscribe my channel and request your friends to subscribe the channel and enjoy mathematics. I wish you all the best. Thank you.